Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, welcome to Technical Session 14E. My name is Amog Dhamdere, and I will be moderating this session. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome all of you to the 11th International Congress on Information and Communication Technology, ICICT 2026. The 11th edition of this conference is being organized in hybrid mode. The physical event was held in London, UK, and the virtual event is being held through Zoom from the 25th to the 27th of February in 2026. I hope all of you will enjoy the knowledgeable and interactive sessions we have planned today. In this particular session, we will be having 6 presentations, and each presenter will be given 12 minutes to present and 3 minutes for questions and answers. And on the completion of 10 minutes, I will be raising a gentle reminder. There is another request for all the participants that all of you please stay connected with us until the closing remarks are given. And if you have any queries or updates, you can write it to me in the chat box. Now, without any further ado, I would like to introduce our session chairs for this particular session. Our session chair for today is Dr. Jane Christine G. Suarez. Dr. Jane Christine G. Suarez is an associate professor at Bulacan State University in the Philippines with over 20 years of experience in academia. Her research interests include information technology, statistical tools, and biometrical analysis, with a strong focus on data-driven research and academic assessment. Ma'am, we welcome you, and I request you to give us your opening remarks.
Thank you, Amag, and good day to everyone. It is already Saturday here in the Philippines, and welcome to this session of the International Conference on Information and Communications Technology, ICICT 2026. It is my honor and privilege to serve as your session chair, and I would like to extend my appreciation to all authors for their commitment, creativity, and contribution to the global ICT research community. And with that, let us begin our session and celebrate the exchange of ideas that continuously drives technology toward a more inclusive, secure, and innovative future. Thank you.
Thank you so much, ma'am. Our next session chair is Dr. Sunil Bhutada. Dr. Sunil Bhutada is a professor and head of the Department of Information Technology at Srinidhi Institute of Science and Technology in Telangana, India. With over 24 years of combined teaching and industry experience, his primary research interests include data mining, topic modeling, machine learning, etc. Dr. Bhutada has published nearly 100 research papers, including 14 in Scopus indexed journals, reflecting his significant contributions to research and academic excellence. We welcome you, sir, and I request you to give us your opening remarks as well.
Good day, everyone. Glad to be here, and I was a bit confused with the timing, but I am happy to be here, and I think this is the first time I am being a session chair for this ICICT 2026. I um, wish all the best to all the participants, and thank you so much for having me here. Thank you.
You're very welcome, sir. Now, without any further ado, we can now move on to the sessions we have planned for today's technical session 14E. So our first presenter today is Ragela Krishna Saketvi. I apologize for any mispronunciations, but he belongs to the Amrita School of Computing in India. And the topic of his research paper is a robust image forgery detection approach using UNet and recompression model. Sir, I request you to kindly unmute yourself and start presenting.
Sir, I hope my screen is visible.
Yes, your screen is visible and you are audible as well. You can start.
Yes, thank you. So, good evening, everyone. This paper titled "A Robust Image Forgery Detection Approach Using UNet and Recompression Model" is mainly focusing on detecting and analyzing digital image forensics using deep learning techniques. In this paper, we explore two complementary approaches, one based on pixel level segmentation using UNet and the other based on compression artifact analysis using a CNN. So this work, we aim to support reliable digital forensic analysis by both localizing and classifying forged images. So the motivation or behind the problem statement is that with the widespread availability of the image editing software, changing images has become extremely easy and common. This poses serious risks in areas such as journalism, legal evidence, verification, and personal privacy. Manual or human-based inspection is often unreliable, especially when images undergo recompression or subtle color adjustments. Traditional forensic methods struggle to generalize across different forgery techniques. Hence, there's a strong need for an automated and robust image forgery detection system that can reliably analyze digital images. So, this paper mainly deals with two types of image forgery. The first one is a copy move forgery, where a part of an image is copied and pasted within the same image, usually to conceal or replicate objects. Since the copied region comes from the same image, it shares similar texture and color properties, making detection difficult. The second type is splicing forgery, where content from a different image is inserted. This often introduces inconsistencies in lighting, color distribution, or compression characteristics. Both these forgery types pose unique challenges and require different detection strategies. And coming to the main idea or key idea behind this paper, so instead of relying on a single technique, our work explores two complementary deep learning approaches. The first approach uses UNet, which performs pixel level segmentation to localize the forest regions within an image, while the second approach is based on recompression analysis, where error level analysis features are extracted and passed through a CNN to classify an image as authentic or forged. By combining localization and classification perspectives, this framework provides a more comprehensive solution for digital image forgery detection. And as for a data set that I've used in this paper, for our experiments, we have used the CASIA 2.0 dataset, which is a widely used benchmark in image forgery detection research. This dataset contains over 12,000 images with both authentic and forged samples, including copy move and splicing forgeries. A key advantage of this dataset is the availability of ground truth masks, which allows us to evaluate pixel level localization using segmentation models like UNet and recompression models. This dataset also includes a wide variety of scenes, improving the robustness of our evaluation. Now, coming to the implementation of the UNet model, to localize the UNet model has been used to localize the forest regions within an image. UNet is well suited for pixel level tasks because of its encoder decode structure and skip connections, which help preserve spatial information. The encoder extracts contextual features through downsampling, while the decoder restores spatial resolution to generate a segmentation mask. The final output of the model is a binary mask, where each pixel indicates whether it belongs to a forest region or not. Now, coming to the UNet training part, before training the UNet model, all images were resized to a fixed resolution and normalized to ensure stable learning. Since color inconsistencies can be a strong indicator of image forgery, we trained the model using multiple color space representations, including grayscale, RGB, individual RGB channels, and LAB channels. This model was trained in a supervised manner using ground truth masks, with binary cross entropy as a loss function and Adam as the optimizer. And the output probability map was then threshold to obtain a binary forgery mask. And finally, to discuss about the UNet result and observations, this UNet model was evaluated across different color spaces. Although grayscale images achieved the highest training accuracy, reliable localization was observed only when ground truth masks were present. RGB images performed very few and often random counters. When individual color channels were tested, most channels failed to localize forest regions effectively. However, the A channel of the LAB color space showed partial counters, particularly around green regions, indicating sensitivity to red-green color inconsistencies. Now, coming to our second approach in our study, which is based on recompression analysis, specifically error level analysis. When an image is recompressed, forged regions behave differently due to multiple compression stages, while authenticated regions follow a consistent compression pattern. By computing the absolute difference between the original image and its recompressed version, ELA highlights these inconsistencies. These error level analysis images are then used as input to a CNN, which learns to classify images as either authentic or forged. Now, coming to the recompression model results, The recombination-based CNN achieved training accuracy of 92.23% and a validation accuracy of 89.10% when using recompensed images at a quality factor of 98%. On further analysis, the model performed particularly well in detecting copy move forgeries, achieving an accuracy of 88.9%. However, it struggled significantly with splicing forgeries, where the accuracy dropped to 36.8%. Additionally, this model showed poor performance when authentic images were passed, often misclassifying them as forged. Now, this indicates that recombination artifacts alone are insufficient to reliably distinguish all forgery types. Now, finally, to compare both these two methods, this table here summarizes the analysis of both the approaches. Here, it could be seen that the unit model is effective for pixel level localization, but heavily depends on ground truth masks and shows limited generalization. And the recombination based model does not require ground truth and performs well for copy move forgeries, but struggles significantly with splicing and authentic images. These observations suggest that neither approach alone is sufficient, and instead, they provide complementary insights into image forgery detection. So, finally, to conclude, this work evaluated two deep learning based approaches for image forgery detection. This UNN model demonstrated the ability to localize forged regions at a pixel level, while the recompression based CNN showed strong performance in detecting copy move forgeries. However, both approaches exhibited limitations in terms of generalization and sensitivity to dataset characteristics. Now, the future work can focus on improving robustness by using larger datasets, incorporating attention, or transformer based models, and combining spatial and compression domain features for more reliable forgery detection. And this brings me to my end of presentation. Thank you for your time and attention, and I'll be happy to take any questions.
Yeah, Krishna.
Thank you for your presentation, sir. I now ask our session chairs if they have any questions for you.
I have one question, Krishna.
Yes, sir.
How does the unit segmentation model handle varying sizes? There are varying sizes of your forged regions, and there are varying sizes of your images also, right?
Yes, sir.
So how does this unit segmentation model handle that?
Just a second. Sir, basically, the QNet handles various input sizes through a combination of fully convolutional design. Like the key idea behind this is that it uses convolutional pooling and upsampling layers, no fully connected layers. So I think unit, because of this, unit can accept any image size as long as
No,
it's
that
large enough to survive the.
error level analysis which you have chosen, it is for recompression, right?
Yes, sir.
And that should improve the CNN's forgery classification performance. Is that doing it, or why that error level has been chosen by you? Okay,
Sir,
no problem. Fine.
should I? Yes.
One
Sir,
thing, other thing, one last question
yes, sir.
is how many authentic and forged images you have?
Sir, as of now, for that in a particular data set, we've had 12,000 images total.
Correct.
So in that,
What
approximately
is the ratio
5,000.
of forged and authentic?
Yes, sir, we have it here. We have it 7 is
Seven
to 5.
five, so yeah, 7.5 and 5.1, something like that. Correct.
Yes,
Now,
sir, 7,
if
7
there
is to
is an
5.
imbalance, how do you handle that? Imbalance during training of the model.
Sir, to be honest, I think that's one of the limitations here, sir. This was actually this two approaches actually heavily depend upon a data set. So
Mhm.
they're sensitive to a data set right now. We have to improve it in the future works.
All right. Thank you.
Dr. Suarez, any questions for our speaker?
None. So, congratulations and thank you for presenting this important work.
Thank you, ma'am.
Thank you so much for your presentation, sir. We can move on to the next speaker now. So our next speaker for today's session is Pubudhi Vitharana. I apologize again for any mispronunciations. And she belongs to Nikto Solutions from Malaysia. And the title of her research paper is ACCM, an advanced cognitive complexity metric for modern Java code bases with machine learning. Ma'am, I request you to kindly unmute yourself and start presenting.
Yes. Thank you. And yeah, can you see my screen and am I audible to you all?
Yes, your screen is visible and you are audible as well, so you can begin.
Yeah. Good day, everyone. So I'm Pubudi Vitarana. It's a pleasure to present at ICICT 2026. Today, I will introduce SECM, an advanced cognitive complexity metric designed specifically for modern Java systems. As software systems increasingly rely on functional and annotation-driven abstractions, traditional complexity metrics struggle to reflect true cognitive effort required for comprehension. So this work proposes a construct-aware and machine learning calibrated framework to bridge that gap. This is the agenda for my session, and moving forward, why complexity still matters. Software complexity directly affect maintainability, fault-proneness, and long-term system evolution. So developers spend significantly more time understanding code than writing. So therefore, measuring cognitive complexity accurately is critical for quality assurance, refactoring prioritizations, and sustainable development. Traditional metrics such as cyclometric complexity measures independent control flow paths and Halstead metric estimate effort using operator and operand counts. While useful, these metrics primarily quantify structural or lexical properties. They do not count for abstraction-driven cognitive effort introduced in modern Java system, actually specifically for Java systems, but in terms of modern systems. Cognitive metrics is improved upon structural metrics by introducing cognitive weights for control structures and nesting. ICB, for an example, accounts for recursion and compound conditions. However, these models remain largely rooted in traditional imperative and object-oriented construct. So they do not implicitly model modern Java abstractions such as streams, lambdas, or annotation-driven execution. The core research gap is that existing approaches do not simultaneously capture modern Java abstractions, model implicit framework-driven complexity, and validate alignment with developer perception at scale. So this gap motivated the development of SECM. SECM extends ICB to maintain theoretical continuity. It introduces construct-aware submetrics specifically for Java 8 features. Additionally, it integrates supervised machine learning to calibrate complexity scoring against human-labeled data. The framework outputs both a numeric complexity score and the interpretable low, medium, or high classification. Those are the three classifications: low, medium, or high labeled classifications. ACM is not just a formula adjustment. So it is designed as a layered framework where cognitive modeling and empirical validation complement each other. The metric formulation captures construct-specific cognitive load, while the ML layer ensures alignment with real developer perception. When it's come to the SECM architecture, SECM is implemented using a modular architecture. First, an AST abstract syntax tree based parser extracts structural and constructor-aware features from Java code. AST-based parsing allows us to analyze structural hierarchy instead of plain text patterns. For example, lambda expressions appear as explicit nodes in the AST, enable us to measure nesting depth accurate. The second is the ACCM engine outcomputes the extended cognitive scope. The third, the supervised ML module, classified methods into complexity categories. Finally, visualization layers supports integration with development workflows. This is the overall ICCM architecture. When it's come to constructor-aware extensions, the primary innovation lies in constructor-aware modeling. So ACCM measures lambda nesting depth and parameter complexity. So it evaluates stream pipeline length and operator diversity. It also models annotation density and dispersion, which reflect implicit framework behavior. These constructs often introduce hidden cognitive load not captured by traditional control flow metrics, such as in ICB. For instance, consider a method with a single return statement but a deeply chained stream pipeline with multiple intermediate operators. Cyclomatic complexity may assign it low score. However, understanding the data transformation sequence may require significant mental effort. So, SECEM captures this abstract driven complexity. To align complexity measurement with human perception, we collect developer label samples from open source Java project. Using these labels, supervised classifiers such as random forest and gradient boosted trees are trained. K-fold cross-validation ensures robustness. This empirical calibration complements the cognitive formulation and improves real-world alignment. By training, so this ML component does not replace the metric. It calibrates and validates it. So this training on developer label samples, ACCM reduces reliance on purely assumption-based cognitive weights. So ACCM is evaluated against established baseline, including cyclomatic complexity, ICB, and SONA-Cube's cognitive complexity. So we measure correlation with developer ratings and classification performance metrics such as accuracy and F1 score. So this allows both quantitative and practical comparison. So ACCM aims to provide stronger alignment with developer perceived complexity, particularly in abstraction-heavy Java systems. It improves detection of hidden complexity and supports maintainability, forecasting, and refactoring prioritization. In conclusion, ACCM extends cognitive complexity modeling to explicitly capture modern Java abstractions and integrates machine learning to align scoring with developer perception. It provides a scalable and human-centered approach to complexity measurements for contemporary systems. So future work includes expanding the dataset diversity and evaluating cross-framework generalizations. So the last, ACCM unifies cognitive theory with construct-aware modeling of modern Java abstractions. Through empirical machine learning calibration, it delivers a scalable and human-centered framework for measuring software complexity. And thank you, and I welcome your questions.
Thank you so much for your presentation, ma'am. I now request our session chairs to ask any questions they might have.
All right, so congratulations and thank you for this well structured and forward looking contribution. So, my question is, could you identify some of the limitations and potential biases of ACCM?
Yes, we do have limitations. So the primary limitation is the reliance on the human label data, which can introduce subjective bias despite using experienced developers and inter-rater agreement checks. So another limitation is generalization across diverse frameworks and coding styles, as abstraction patterns may vary between different domains. This ACCM models modern Java construct evaluating language features that may require periodic update and retaining of ML machine learning components. These are the represent ongoing future with the limitations.
Yeah, good presentation. One question from my side. How
Yes.
does ACCM's output differ from the regular metrics like cyclomatic or complexity, cognitive complexities you mentioned, right? How does the output differ? Is there any change between the outputs?
Yes.
What would be the change? I mean, have you checked both outputs? Is there any
So
major difference?
yes, there's a different because ACCM differs from ICB in two major ways. So first one is the ICB focuses on traditional control structure, weighting such as nesting, recursion, and compound conditions. But ACCM explicitly model modern Java construct like stream, pipelines, lambda nesting, and annotation-driven behavior. The second, ACCM integrates supervised machine learning to empirically align complexity scoring with developer perception, which ICB does not include, so that the ACCM is construct aware and empirically calibrated extension of ICB. That's the um, two major differences between ICB and ACCM.
All right. Any plans in the future to make an alternate model?
It is included in the future work, sir.
Yeah, yeah. So in future works, are you going to plan for an alternate model apart from the regular one which you are doing right now? It should be there, right?
Yeah, yes.
All right. Thank you.
Thank
Thank
you
you
so
very
much
much.
for your presentation, ma'am. We can now move on to our next presenter for this session. So our next presenter is Mohammad Shah Jalal Ahmed from the Jagirnagar University in Bangladesh, and the title of his research paper is Early Identification of Non-Alcoholic Fatty Liver Disease with its Associated Causes and Risk Factors in the Selected Area of Dhaka District in Bangladesh using Statistical and Machine Learning Analysis. Sir, I request you to kindly unmute yourself and start presenting.
Assalamu alaikum everyone. I am Shahjal Ahmed Akash from Jahangirnagar University, Dhaka, Bangladesh. My research topic is early identification of non-alcoholic fatty liver disease in Dhaka district. We know that non-alcoholic fatty liver disease is the leading cause of liver disease globally, with rising prevalence in urban Bangladesh, especially Dhaka, is strongly linked with obesity, diabetes, metabolic syndrome, and unhealthy lifestyles. in Bangladesh, around 1 to 3 people are suffering from NFLD. NFLD often remains undiagnosed and until advanced stages. Traditional diagnostic methods are costly and practical for mass screening. This study leverages community-based data and combines statistical and machine learning approaches to identify key risk factors, enabling early detection and effective risk stratification. My objective is to apply statistical and machine learning techniques to Dhaka districts to detect non-alcohol fatty disease along with its risk factors and related causes. In this study, I use statistical analysis like ICICT test, t-test, ANOVA, identify major risk factors. Besides, I conduct SVM exhibits and logistic regression to determine which one performs best and compare those among those models for NFLD detections. I also conducted SHAP to find out the risk factors. I mainly collected data from 3 hospitals. I collected 120 samples. The hospital, I there asked patients and collect data through multi-random sampling. The study population is adults and who their age is 18 plus. I conducted this research study around 4 months. I use this SPS 25 for statistical analysis and Google Colab and PyCharm for others analysis. Here model validation for 10 test split 10 test has been used for model validation and k-cost validation also used. I use SHAP for identify the identify the risk factors. SHAP is a explainable AI technique based on game theory, which detects global and individual risk factors. So here I found that systolic blood pressure, diastolic blood pressure, and triglyceride, total cholesterol, LDL, HDL, etc. are associated through ANOVA test and t-test. I also conducted SHAP measurement, which I found through which I found out the risk factors. From SHAP, SHAP, I found out that yes, TZ, income, SBP, high pressure are the most indicative factors which affect all 3 classes. And here others fried food and liver stiffness, stones are thyroid disorder, smoking. That's are negligible to count. In my in my research found. Here is the. I also conducted Rockock graph. In this Rockock graph describes that logistic regression, random forest, Stafford vector machine, random forest, and XGBoost are the are perfect to conduct conduct and predict
Mr.
NFLD.
Shahjalal, can you just make it full screen, the PPT? Sorry for interrupting. Can you make it full screen?
Uh,
Okay, no problem. Carry on, carry on.
Sir, is my voice audible?
Yes, you are.
Sir, you can continue with your presentation.
Through Rockcraft, we found that LR, XGBoost, and random forest are the perfect for predicting NFLD. The score of Rockcraft of XGBoost and logistic regression is 1, and random forest is 0.99. Here is the accuracy, precision, and recall and F1 score on AOC and log loss curve score of FD models. From the models, we can see that gradient boosting and decision tree have achieved the 100% accuracy level, while logistic regression and random forest have achieved 92 and 93% accuracy level. Among them, log-log curve is gradient boosting and decision log-log score is 0.00, and random forests logistic regressions log loss score is 0.1410, and support vector machines log loss score is 0.160. Though this log loss score is lower, and that's why decision tree and logistics is the perfect for predicting NFLD, and random forest and SVM can be alternative for or predicting NFLD in this cases. Uh, so my so my statistical analysis that grade 1 was 54%, grade 2 is 40%, and grade 3 is 6.8%. Among them, 70% is male and married, and others are 6% and 30% are female and unmarried and female. Most of the mostly are middle-aged people, which ages are 3150 to 50 plus. We have found that diabetes, hypertension, and overweight is among them. Significant correlations is lower HDL, higher blood pressure, BMI, triglyceride, LDL, blood sugar, LGBT are associated with causing NFLD. Key predictors from SHAP analysis: high blood pressure, diabetes, overweight, dyslipidemia, and income. Top models and gradient boosting, disease tree, most effective. Alternate model, logistic regression, SHAP analysis. Stable, simple. Are identified average influence features on multi-class NFLD predictor, grade 1, grade 2. It was first study using SHAP for multi-class NFLD prediction. First study implementing and GUVS interface for NFLD prediction. For High incidence of NFLD in Bangladesh is a major public health problem. Strong links found between NFLD, obesity, hypertension, and poverty. This ML technique indicates the potential for data-driven scheme method to guide prevention efforts, especially allocate resources and enable earlier identification of high-risk individuals. This finding underscore the importance of public health programs for NMLD as a vital component of broader metabolic health initiatives. Data-driven screening can improve resource allocation and identify at risk individuals sooner. So recommendations. My research has also some limitations. I have the limitations are my sample size is small. It was only 412. If it is higher than 700 or 80 or more, I think it will easy to predict NFLD is it more across the country, and I only contacted on Dhaka district of the hospitals of Dhaka district. There are 63 districts left in our country. So if I conduct a if people conduct a study broader in the broader country, then I will maybe find out the actual scenario of NFLD prediction. And thus diabetes overweight, SBP, LBP are the factors of causing NFLD. So we should government should implement national programs within the country for broader metabolic health initiatives, and a national health program should be implemented. Thank you, everyone.
Thank you for your presentation, sir. I now request our session chairs to ask you any questions they might have.
All right, so congratulations and thank you for this significant and timely presentation. So my question is, based on your study, so what are the top predictors for NAFLD, and does it included in the SHAP analysis and interpretation, which is very crucial when we translate model outputs into public health recommendations?
The top predictors or for NFLD is blood pressure and income. This is the top risk predictors of NFLD, and this can be thus we can thus we identify fixed risk factors for NFLD in the people of Dhaka district in the people of Bangladesh. So we can say that these risk factors are vital for causing NFLD in Bangladesh. So if we mitigate these factors, then we can stop preventing fatty liver disease and other liver related chronic diseases like liver cirrhosis, chronic diseases. That's why awareness program should be conducted, stopping our people to stop eating fast foods, or our people to run at least run or walk at least 1 or 2 hours in a day, eating healthy foods and foods that are beneficial to their health and their liver, arranging national marathon program, etc.
Dr. Bhutada, any questions for our speaker?
No questions. Thank you.
Okay, thank you so much for your presentation, sir. We will now be moving on to our next presenter for today. So our next presenter for today is Ekta Choda from the Symbiosis International deemed to be university in India. And the title of the research paper is From E-Governance to Trust-Centric Digital Government, an institutional trust and technology acceptance perspective on AI and blockchain-enabled governance in India. Ma'am, I request you to kindly unmute yourself and start presenting.
Yeah, I think I can share it now. Just give me a second, please.
Sure, sure.
Let me know once you can view my screen, please.
Yes, your screen is visible.
Okay, just give me a second. I'll just open the presentation. And I am sorry for so many windows, but I think, okay, this is good. Is it viewable?
Have you started this slideshow because it appears your screen is frozen?
Yeah, I have started the slideshow.
We are still able to see the non-slideshow screen. So can you try to share your screen once again, please?
Is this okay? Yeah,
No, no, your screen is moving now. So yeah.
Is this fine?
Yes, ma'am, you can continue like this as well.
Then I won't be on slideshow. Is that okay with everyone then?
You can start the slideshow, please. Can you do it for me?
Okay, I'll do it. Is this okay? I think it takes, there's a lag. Just allow it a minute or like a few seconds.
Okay, I'll wait.
Can you see it now?
I am still not able to see it in the slideshow, but I can see your slides perfectly.
Okay, then we'll continue like this if that's okay. Maybe the slideshow.
Yeah, sure.
will show up.
No, you can go ahead. You can continue like this.
All right. Good evening, everyone. The topic or the study examines a fundamental question in digital governance, which is why does digitization not automatically translate into citizen trust? Oops, I'm sorry. I think something is not falling in place. Just a second. It just got dropped. Okay. I'm really sorry about this, but let me know if you can see it.
It's fine, ma'am. Your screen is visible, but yeah, it's now completely visible.
All right.
Yeah.
So over the past 2 decades, governments have invested heavily into e-governance platforms to improve efficiency and accessibility. While operation improvements are evident, trust outcomes always remain inconsistent. We argue that this disconnect exists because trust is institutional and not transactional. So, what are we trying to say in our introduction and research objectives? So, traditional digital transformation focuses on speed, automation, convenience. However, citizen trust depends on transparency, integrity, procedural fairness. With the emergence of AI and blockchain technologies, digital government is moving towards what we call today is trust-centric digital governance. So, what do our research objectives actually study to examine? It's basically to examine how e-governance, AI governance, and blockchain governance jointly influence citizen trust, analyze the mediating role of service efficiency and transparency, investigate the moderating role of the rural-urban digital divide, develop and empirically validate an integrated institutional trust TAM framework in the Indian context. What does our review of literature and hypothesis development speak of? E-governance research shows strong efficiency gains but mixed outcomes. AI governance enhances responsiveness and predictive decision making, but trust depends on explainability and fairness. Blockchain governance is increasingly described as a trust infrastructure because it embeds transparency and immutability in the administrative systems. So from a theoretical lens, institutional theory explains the legitimacy formation. Trust theory defines competence and integrity as core trust dimensions. TAM explains perceived usefulness and adoption behavior. However, existing literature rarely integrates all perspectives into a single empirical model. What does a hypothesis propose? The hypothesis H1 and 2, e-governance and AI enhance service efficiency. Hypothesis 3, blockchain enhances transparency. 4 and 5, efficiency and transparency positively influence trust. And 6, the urban-rural digital divide moderates trust outcomes. So the key argument is that technologies influence trust indirectly through institutional mechanisms. For the research methodology, we have taken a sample base of 312 citizens across 5 different states of India. We used validated measurement scales adapted from prior literature and measured all constructs on a 5-point scale. The key constructs include e-governance, AI governance, blockchain governance, service efficiency, transparency, and citizen trust. We have employed structural equation modeling, that is SEM, mediation testing, multi-group moderation analysis, which is the comparison between our rural and urban, rural versus urban. This allowed us to examine direct, mediating, and moderating effects simultaneously. What does the analysis and hypothesis testing say? I'm sorry. What do they say? AI governance, the key findings say that AI governance significantly enhances service efficiency. Blockchain governance exerts the strongest effect on transparency. Both efficiency and transparency positively influence trust. However, transparency has a stronger impact on trust than efficiency, is the critical insight that we have deciphered. It suggests that citizens value visible integrity and fairness more than speed alone. Mediation results. Efficiency partially mediates the technology trust relationship. Transparency strongly mediates the blockchain trust relationship. Moderation results. The rural-urban digital divide significantly moderates trust formation. Urban citizens demonstrate stronger trust translation compared to rural population. What have been the key findings and contributions? Digitization, for us, the key findings are digitization alone does not generate trust. Transparency is a stronger trust driver than efficiency. AI enhances competency perceptions. Blockchain strengthens institutional integrity. Digital inequality weakens trust outcomes. Sorry. Theoretical contributions integrates institutional theory, trust theory, and TAM into one model. Empirically reframes blockchain as a legitimacy mechanism, establishes transparency as the dominant institutional mediator, positions digital inequality as boundary condition in trust formation. What are the practical implications? Policymakers must move beyond automation, embed explainable AI, implement blockchain for auditability, and design inclusive digital systems. Trust must be designed into governance architecture. To conclude, our study demonstrates that trust-centric digital government emerges not from technology adoption alone, but from institutional embedding, transparent governance design, and inclusive implementation. Efficiency builds operational confidence, transparency builds moral confidence. Without inclusion, digital transformation may reinforce distrust rather than reduce it. So therefore, the future of digital government lies in aligning intelligent technologies with institutional legitimacy and equitable access. The key references have been called out, and at here I would like to conclude my presentation. Thank you very much. Happy to have any questions coming in.
Yes, it,
Thank you
one
so much for
question.
your. I'm so sorry, sir. You can continue.
No problem, no problem. Fine.
Yes.
Sir, you can continue asking your question.
Yeah, one question. Ekta, efficiency alone does not guarantee trust. That is what you said, right? Could you emphasize on that? What is that?
Yes. So, as the presentation explains, that while the audience is very inclusive to use technology, it is just not about the speed and efficiency of a technology or of a system, but transparency is something which is one of the key foundations which enables larger utilization of a technology where it's transparent, intuitive, and as it's transparent, it therefore helps in building trust. So that's what we're trying to speak of.
And how does AI
Sorry, so because as I also understand that trust is not only about very fast services. When we speak of transparency, it's also about how fair it is and how integral it is. We should know what we're trying to use is where our data is getting leveraged or it's getting used. Is it going in the safe and the right hands?
Another one is how is what is the difference between AI and traditional method of the e-governance?
So when we speak of AI definitely, sorry, very sorry. When I'm talking about AI, AI today is integrated with a lot of there are multiple how do I say? There are multiple kind of key factors which go into an AI. AI is not about just it's not like a very straight jacketed kind of technology that is being used. It's got multiple services. AI is not just like one particular thing where it can be used into it's an intuitive methodology which can be utilized into multiple facets. When I talk about traditional e-governance, it is about a colloquial system which has been developed, and there is a typical process which is going to be straitjacketed. This is the way it is going to be followed, and there cannot be much of permutation combination there. The systems are lesser intuitive. The systems are lesser intuitive. The speed, the process, the efficiencies are not equipped the way they are in an AI system and a process.
All right, thank you.
AI basically and primarily the AI enhances only administrative competency and efficiency, but traditionally e-commerce is very colloquial way of managing an e-commerce governance system.
Yes, thank you.
Dr. Suarez, any questions for our speaker?
None. So congratulations and thank you for presenting this conceptually rich and policy relevant study. Thank you.
Thank you very much. Thank you.
Thank you for your presentation, ma'am.
Thank
We
you.
now move on ahead with our next presentation for this session. Our next presenter is Sunei Kim from the San Jose State University in the United States of America. And the title of the research paper is Graph HTAP Bench, an HTAP benchmarking framework for graph databases using healthcare workloads. Ma'am, I request you to kindly unmute yourself and start presenting.
Thank you. Good morning. My name is Sunny Kim. Today, I will present Graph HTAP Bench, HTAP benchmarking framework for evaluating graph databases using healthcare workloads. Here, HTAP stands for Hybrid Transactional and analytical processing. Healthcare data is naturally highly connected. Patients, diagnosis, providers, and procedures are all linked. Graph databases are well suited for this kind of data because they efficiently represent and traverse complex relationships. Modern healthcare applications must handle two workloads simultaneously: transactional operations, such as updating or retrieving patient records, and analytical queries, such as cohort discovery for clinical trials and care path analysis to study sequences of clinical events. Traditionally, OLTP and OLAB workloads are handled by separate systems. This separation increases operational complexity and introduces delays due to data movement and preparation. HTAP systems address this by allowing analytics to run directly on fresh transactional data within a unified single system. Because HTAP systems are very expensive to deploy, benchmarking them under realistic workloads is critical. However, most existing benchmarks focus on relational databases or aggregate-oriented NoSQL systems. Graph benchmarks exist, but they typically model social networks which do not reflect healthcare data. Even when graph HTAP evaluations are available, they are often system-specific, making comparisons difficult. This motivates the need for vendor-agnostic, graph-native HTAP benchmark grounded in healthcare scenarios. This slide shows the healthcare graph model we developed. We transformed the ORDA health record dataset into a graph model and just use it as a uniform schema across graph databases under test that include Neo4j, memgraph, and Janus graph. The model preserves clinical semantics, temporal relationships, and especially natural data skew, enabling fair evaluation of indexing and query performance. Graph HTAP Bench organizes workloads into three categories. OLTP includes 7 transactional update and lookup queries. OLAB includes OLTP includes 7 and OLAB includes 3 scan and aggregation heavy queries. And we have a separate category called graph that includes 7 multi-hop pattern-centric traversal queries. All workloads are defined using JSON templates, as you can see in the example on the slide, and instantiated as Cipher for Neo4j and memgraph, and Gremlin for Janus graph. Cipher and Gremlin are a query language for the given graph databases. Graph HTAP Bench supports 2 execution modes. In closed mode, a fixed number of workers issue queries sequentially, so the arrival rate depends on execution time. In open mode, queries arrival following a Poisson process, which better reflects real-world traffic. We evaluate performance using 3 metrics: throughput, latency, and freshness. Throughput measures steady-state query rate. Latency includes average and the 95, 99th percentile latency to capture tail behavior and interference effects. Freshness measures how long it takes for a transactional update just made to become visible to analytical queries. This figure shows the architecture of graph HTAP bench we developed. Central benchmark runner configures and coordinates the experiment. Queries are generated from query template placed into workload-specific queues, such as OLTP queue, OLAP queue, and graph queues, and executed by client workers customized for individual system under test and measured by a central aggregator. We evaluate 3 representative graph databases: Neo4j as a native graph, Neo4j that uses native graph engine, memgraph as an in-memory graph database, and Janus graph, which relies on distributed backend such as Cassandra. Experiments are conducted on AWS EC2 with both single node and clustered deployments. We used equivalent graph model schemas and functionally equivalent indexes. This slide shows the impact of analytical workloads on OLTP performance in a single node setup. In both graphs, the x-axis represents the number of OLAP worker in the left graph and number of graph workers in the right graph. And y-axis is OLTP throughput. OLTP configured to consume about 70% of system capacity. In x-axis 0, there is no analytical workload, so that it serves as a baseline. Neo4j, present in blue line, shows a notable throughput drop and significant tail latency inflation, as you can see in the table and the column labeled as 20. This indicates intensive resource contention. memgraph in yellow line performed well under mixed workloads with only slight throughput degradation and stable latency due to its in-memory execution. Janus graph in red line struggles a lot under OLAP workloads, as you can see from the left graph. In red line, throughput drops to 0 and the system crashes. That's because global intensive scans place heavy load on its back-end database. Graph workloads are less severe for Janus graph, as you can see from right graph in red line, because graph traversals are localized and much lighter than OLAP, massive OLAP scans. These results show that architectural design choices strongly affect HTAP behavior, even under identical workloads. This slide examines scaling effects. In the left graph, x-axis represent the degree of workload mixes. 0/0 means no analytical workers. And the 20/20 is highest workload mixes, where 20 OLAP and 20 graph workers. The first set of 3 lines in the left graph are from memgraph, and the second set of 3 lines are from Janus graph. So let's focus on left graph. Blue line in the first set and orange line in the second set are captured in the single node setup.
Excuse me, ma'am.
Yeah.
Apologies for interrupting, but you are left with 2 minutes of presentation time.
Okay. All right.
Yeah, thank you so much.
as analytical workload increases, OLTP throughput drops sharply on single node. And we can see the same data in different angle. As we scale the cluster, this interference is significantly reduced. Under heavy mixed workload like 2020, scaling brings OLTP throughput as close to baseline level, showing that effective workload distribution can mitigate HTAP interference. Finally, we examine the trade-off between scalability and freshness. MEM graph, the top graph is about scalability and bottom graph is about freshness. MEM graph maintained stable freshness, as you can see in the red line in the bottom graph, around 500 milliseconds, but does not scale as effective. Janus graph scales better with more nodes, but incurs higher coordination overhead, resulting in freshness closer to 1 second. This highlights fundamental trade-off between throughput scalability, and update visibility. In conclusion, HTAP performance depends heavily on architecture, concurrency, and cluster size. Graph HTAP Bench provides systematic and reproducible way to evaluate these factors. Looking ahead, we plan to expand workloads, increase concurrency, evaluate additional systems, and integrate real-time healthcare analytics such as streaming and predictions. Thank you.
Thank you for your presentation, ma'am. I now request our session chairs to ask any questions they might have.
Congratulations and thank you for this highly technical presentation. So my question is, how adaptable is Graph HTAP Bench for healthcare institutions with significantly different workload scales, such as a small clinic versus a national hospital?
That's a very good question. So this presentation is about expandability and reusability of this framework. So to address different type of workload, such as different types of data set, the only thing we can do is converting that data set to the corresponding workload system can recognize. And this framework supports that expandability. So that's a matter of availability of data. Sometimes it's very hard to obtain the data itself because healthcare data is very private and proprietary. But as long as data is available and there is a target system, converting that and plugging into the system is given.
All right, thank you.
Yeah, ma'am, good evening and wonderful presentation.
Thank you.
And the thing I liked is about your architecture. In the architecture, you have mentioned that a query generator and there is an benchmark runner, right? How do they both interact with each other? If you see
I
the
didn't hear the
architecture.
architecture, so
Yeah,
I didn't hear the what is that? Name of component you are interested. What is the name of component you are interested?
query generator and
Yeah, query
benchmark
generator.
generator.
Yeah,
Yes.
so query generator is just generalized so that as long as we can fill this template with specific query language that
Basically, I
translates.
want to know the difference between open mode and the closed mode. That's it.
Open mode and closed mode. Yeah, thank you for the question. Open mode is to simulate realistic arrival rate with the Poisson process. So if we specify the average arrival rate, it automatically spawn the queries according to inter-arrival rate we specified. Closed mode is we just fix the number of client workers so that those workers keep fetching query and execute the workload query sequentially. so that we can preserve fixed number of workers in the system.
And PII must be a constraint.
Which
PII
one?
data, personally
VII?
identifiable. Yeah,
What is the
I mean
VII?
P for personal privacy, identifiable information.
Oh. So again, this work is limited. If data is available, we can adapt that. And the
Correct.
privacy of data, security of data is not the scope of our research. It's beyond the scope.
All right. Thank
Thank you.
Thank you so much for your presentation, ma'am. We can now move on to the last presentation for this session. Our last presenter for this session is Pushkar P. Urs from the PES University in India. And the title of his research paper is Latent Blending for Long Video Generation Using Diffusion Models. Sir, I request you to kindly unmute yourself and start presenting.
Yes, just a second. I hope my screen is visible.
Yes, your screen is visible and you are audible as well, so you can start presenting.
Yes, hello, I am Pushkar from PS University, and I will be presenting our project, Latent Blending for Long Video Generation using diffusion models. The first question that we must answer is why long video generation? Consumption of videos over the world has exploded in recent years. This is mainly because of platforms like YouTube, Instagram, etc. And there is also an increased reliance in videos as a primary communication medium. Open source video generation models are usually not able to generate videos of the required quality or length for these purposes. The main challenges arise from the fact that open source video generation models are mainly trained on 5-second video text pairs, and this is an inherent problem with them where they can't generate videos of over 5 seconds. We will look at a couple examples on the next slide. So when we talk about the failure of video diffusion models, we can see that these two are actually GIFs of a 10-second video, but we almost see no motion over here because this is beyond the capability of video generation models. We are supposed to see the clouds parting and a waterfall coming into view on the left and a drone moving through the cityscape on the right. But we can barely see some moving water and some cars. And another thing is that in these videos, when the length exceeds 5 seconds, we also see a lot of repetition, which is not really clear in this example. But if you do look closely, you can see the same white car move through the road on the right. Anyway, moving on, some related works. I must mention DIT control, which is where we got our um, where we got the idea for the latent blending approach. Then we also have analysis of attention maps, and of course, an extremely important work in the diffusion space called diffusion transformers for scalable video generation that basically replaced the earlier unit architecture that was used for denoising with diffusion transformers. And this, we have used the WAN 2.2 video generation model, specifically the 5 billion TI2V model for generating videos. This is just a basic structure of the model. Basically, it consists of diffusion transformer blocks for denoising the video in latent space. And before we move on to the latent blending component, here's a small look at the cross-attention maps in WAN 2.2. The specificity with which the text tokens attend to spatial locations in the videos, they slowly decrease and then they increase. And this is seen across both layers and time steps. This was an interesting observation that we made, so we have included it in our paper. And finally, our proposal is that we are basically looking at a multi-clip long video generation pipeline where instead of simply conditioning every subsequent video on one frame from the previous video, we also use some of the latent frames. This is so that we are able to transfer more spatial and temporal information between videos, and we find that this greatly improves the prompt adherence of the overall video. So the methodology basically involves taking a prompt and expanding it into two or more highly descriptive detailed prompts using an LLM. We generate the first video in a vanilla T2E manner and the second in an I2E manner while conditioning the first few latent frames with the last few latent frames of the previous model. I will explain exactly how that happens in the next slide. And yeah, this is basically it. This is our blending architecture where we take the final three latent frames from the first video and we noise it and use them as our first three latent frames for the second clip. We have the formula for the same here where alpha refers to the signal to noise ratio or the latent to noise ratio. This is extremely important as video generation models or any diffusion models for that matter are inherently trained to go from Gaussian noise to whatever your prompt describes. So if we just use the latence in its denoised form, it will not give us a coherent output. It will just mainly be a lot of noise. And then we have a few examples. On the left, we can see the vanilla pipeline. The first 5 seconds are the same for both. On the right, the latent blending pipeline, where we can clearly see detergent being placed into the washing machine. Though technically it's supposed to be poured, both videos just have a bottle of detergent. But on the left, we can see that the detergent just appears out of nowhere from the washing machine and is kept into the basket instead of the washing machine itself. And we can also see the person clearly pressing the start button on the latent blending pipeline. Next, we have a video of a blacksmith. Again, the first 5 seconds are the same, but in the second 5 seconds, we can just see some tongs on the left side, no clear hammer. But in the latent blending pipeline, we can see the hammer clearly in the second clip as well. And finally, we have an animated video. It's a pixelated corgi. The first 5 seconds barely have any motion, but we can see the pixelated bark text on the right, which is not seen on the left. This was included in the prompt. So yes, overall, we see an increase in prompt adherence. These are some of the metrics. This is from the VBent suite. We do see an improvement in image quality, smoothness, flickering, and consistency, but a drop in aesthetic quality and dynamic degree. If you noticed, there was a slight change in the color of image, sorry, in the frames as we moved from clip one to clip two. And the dynamism also decreases in some cases, and we can see a significant, we don't really see a smooth transition between the two videos. These are a couple of the limitations. We have another qualitative benchmark here using Quen VLM, where we do see a small but consistent improvement in the average score. And this is a human preference study where basically if we uh, this was basically a survey given to about 20 people, and if 7 to 13 people could not were if one video was preferred by 7 to 13 people, we kept that under the no preference uh, heading because we felt that such a small difference in the number of people preferring one video really would not be able to tell us anything about which video is actually better. But we do see that the latent blending pipeline is preferred in about 46% of the cases, and the vanilla in about 32% of the cases, if I'm not wrong. Then we have the effect of hyperparameter variation. So we basically have two hyperparameters, K and alpha. Let me just go back to the formula. K represents the number of latent frames that we take from the first video and noise it and use it as the starting few latent frames of the second. And the alpha represents the latent to noise ratio. We found that as K increases, there is a greater noisy segment in the starting of the video, which will have to be removed. And a K value of 3 was found to be most optimal in this case. And with respect to alpha, uh, a lower value of alpha, which meant a lower amount of noise, led to increase in artifacts in the video. We found that an alpha of about 0.85 was the most effective, and this is all specific to the WAN 2.2 model. And yeah, in conclusion, this is basically a training-free pipeline to improve video generation, especially long video generation, based on the WAN 2.2 model. And we have qualitative benchmarks on the VBench suite and Quen. Thank you.
Thank you for your presentation, sir. I now request our session chairs to ask any questions they might have.
All right, so congratulations and thank you for presenting this forward looking and technically ambitious work. My question is, how does your approach handles challenges such as, for example, scene transitions, motion drift, or accumulation of latent errors over long durations?
Yes, we did try this over long duration. We tried it for about a video of about 20 seconds. So that's 4 5 second clips. And we found that the noise sort of adds up. As we could see in this clip, as I showed you, the starting few frames of the videos are pretty noisy and unusable. And this length was greater in subsequent videos. And it was also a sort of prompt by prompt basis where some performed well for 15 seconds and some didn't. But up to the 20-second mark, it wasn't really that great.
All right, so thank you.
Dr. Bhutada, any questions for our speaker?
Yeah, one question. Interesting topic. What is your core innovation? I mean, latent blending architecture is there, but apart from any industry related, or what is that? How it is going to be used
It's
in?
nothing industry related as such because this work is only a very small improvement. I don't really see an exact industry application for this, but we do hope that this, since it is training free, it can be used with a lot of other models, and we do hope that with other innovations, this will add up in the future.
So, any kind of difficulty you faced when you were trying to lengthen the video or shorten the video?
Difficulty in short in the video, not really, but yes, of course, length in the video is always difficult. That is one of the inherent problems with video generation models. And other than that, I guess GPU time.
Yeah. All right. Okay. Wonderful. Good. Thank you.
Thank you.
Thank you so much for your presentation, sir.
Thank you.
And that brings us to the end of technical session 14E. I now request our session chair, Dr. Jane Christine Suarez, to give us her closing remarks.
All right, so thank you to all of our presenters and participants for a highly productive and meaningful session. And I would like to acknowledge also the organizers of ICICT 2026, the Global Knowledge Research Foundation, and GR Scholastic for creating this dynamic platform where academic excellence and global collaboration continue to thrive. To all our presenters, your efforts, insights, and scientific rigor are truly appreciated. And with that, I formally conclude technical session 14E, and I wish you all continued success and hope you enjoyed the remaining sessions of ICICT 2026. Thank you.
Thank you so much, ma'am. I now request our session chair, Dr. Sunil Bhutada, to give us his closing remarks.
Thank you, all the participants, and it was great to have some wonderful presentations. I thank Professor Jenny as well for sharing the session chair, co-session chair with me, and some good takeaways and some good innovations and some good presentations were there. And all the very best for the future for all the presenters, and congratulations to everyone. Thank you.
Thank you so much, sir. I sincerely thank all our authors for their excellent presentations and contributions in this session, and all our participants as well for being a part of this international conference. I hope this session was informative enough for all of us. And on behalf of the entire team of ICICT, I thank all of you for your continued support for this 11th version of ICICT. And of course, we will be more than happy to host all of you once again for the 12th version, which will be happening in 2027. Just a quick announcement for all the presenters. You would be getting your digital certificates via email within 2 working days, and the publications will be live within 7 to 8 months. So kindly cooperate with the team of ICICT. And once again, I would like to thank both our session chairs for chairing this session. Just a small token of appreciation on behalf of Team ICICT. So we thank you for your valuable presence. Just a small request to all of you. Can you please switch on your cameras for a quick snapshot of this virtual conference? I'm so sorry. Yeah. I think we're done. So yeah, thank you everyone. Stay safe and take care.
Yeah, thank you, Dr. Sunil. Thank you.
Thank you and bye-bye. Thanks.
Thank you, Amog.
Thank
Thank you.
you.
You're
It is
very
very
welcome,
nice
ma'am.
meeting you.
Yeah, thank you
Have a
all.
nice day.
Bye. Bye-bye.
Thank you.
Bye.
Bye.